Hi, this is an introduction to logic. I'm Mark Thorsby, and this course overviews the basics of categorical, propositional, and predicate logic. Today we're starting our session on predicate logic, and in particular we're just going to be covering what the basic symbols are, what the translation is, and what the differences are between propositional and predicate logic. Let's see here, let me make this full screen. Welcome back, everyone. For those of you who've been watching the videos, I apologize. In our last couple of videos here, my technology was broken. I had to go buy a new pen here. So fortunately, that pen came in, and we're ready to start our video series here. Okay, so what I want to talk about today is predicate logic, but before we sort of begin to talk about what predicate logic is, whoops, get my pen, there we go. Before we begin to talk about what predicate logic is, let's sort of do a brief review. You'll notice I typically like to start off with a brief review. But my review today is going to be a little bit different in the sense that let's begin by reminding ourselves, well, what exactly is logic, right? And why should we actually study logic? Well, logic is the study of arguments. And the reason we should study logic typically is so that we have the capacity to analyze complex arguments before we make our decisions on what we should believe and or how we should act. So logic is important for that reason. Now, if logic is the study of arguments, let's sort of remind ourselves in terms of the review what the main sorts of logical systems we've looked at. We've looked at two major logical systems. The first logical system we looked at here was categorical logic. And some of you watching this video didn't see all of our videos, but the thing to remember here is that categorical logic essentially treats the logical relations between statements that make universal or particular claims. Right? For instance, the claim all S or P, right? If I say, for instance, all lions are mammals, right? That's a universal claim, right? Or if I said that some lions are ferocious beasts, right? That would be a particular claim, okay? The other thing you notice about categorical logic is that the root element, what I was referring to as the core units or the atoms, are terms, right? In categorical logic, that's the principal thing you look at here are the terms. For instance, S is a term, the subject term, the predicate term. We also discover there's a middle term, so on and so forth. There's major, minor, on and on and on. We won't talk too much about that. But one of the problems we found with categorical logic, and this is also referred to as classical logic because it's the oldest form of logic that goes all the way back to Aristotle. But the thing to remember about categorical logic is categorical logic, first off, really requires particular or universal claims to be made. And it also requires us to analyze the terms of statements. But the problem is a lot of the arguments we actually do make in ordinary life don't look like this at all, right? And this creates a big problem for us. So that led us to the second major logical system that really comes sort of around the time of Leibniz, and this is what we can refer to as propositional logic. And propositional logic does not treat of universals or particulars. Instead, propositional logic it looks at sort of the main operators or connectives, right? The main operators or connectives between propositions to discover what inferential patterns that lead to validity. And whereas categorical logic uses terms, propositional logic, well, uses propositions. And we symbolized our propositions with single capital letters, like F can stand for Philippe likes ice cream or something like that, right? And so, for instance, you could say, if Philippe likes ice cream, then Claire will eat strawberry ice cream or something like that, right? And so propositional logic sort of took a look at these. These are the connectives. This is a conditional operator. And then each one of the propositions is symbolized with a capital letter. And propositional logic really gave us a fabulous tool set for really doing a lot better in terms of analyzing ordinary language arguments. But one of the things we're going to see today is that neither of these is actually sufficient for every type of arguments. There are some arguments that simply propositional logic lacks the capacity to analyze, as well as categorical logic. And so today we're going to introduce a third logical system, and we're going to call this predicate logic. But I should say that this is often referred to as first order logic. So some textbooks refer to this as first order logic. And I'll say this is that predicate logic, or first order logic here, this is really the pinnacle, not the pinnacle, but it's really the key logical system that's utilized today. So we would say that propositional logic sort of had its heyday maybe in the later 19th century, early 20th century. Categorical logic is medieval and ancient. Predicate logic today really is the principal form of logical system that's utilized. Now, one of the reasons that we've taken our time in getting to predicate logic in this course is because we're going to see that predicate logic really combines the most important elements of categorical logic and the most important elements of propositional logic together, which means that we're going to be able to use our basic logical operators, and we're also going to be able to analyze particular universal claims. But you're going to see here, instead of propositions and instead of terms, our basic unit here is going to be predicates, right? Predicates. Now, before I get into all of this and begin to explain it, let me show you an example of an argument from the textbook here that cannot be found valid using propositional or categorical logic. And here's the argument here, right? And since the 11th edition, they've updated this. It used to be Julia Roberts, but now it's Catherine Zeta-Jones, right? So Catherine, sort of a dig against Julia Roberts, I guess. Though she's certainly beautiful, and I assume she's rich. So, but here's the argument: Catherine Zeta-Jones is rich and beautiful, right? That's the first premise. The second premise is, if a woman is either rich or famous, she is happy. Therefore, Catherine Zeta-Jones is happy, right? Now, you can see here that obviously we couldn't use categorical logic here, right? We'd have to sort of almost force it into categorical form, but it doesn't work. And actually, if you symbolize this using propositional logic, it doesn't work either. So what we need to do is we're going to see that predicate logic, right, of course, allows us to do this. Now, let's go back here to our sort of thing. Let's start off with here, well, what exactly is a predicate? And you're going to see that a lot of today's lesson is going to be a lot of explanation. I'm going to try to go through this slowly with you. But the first thing we need to look at here is the predicate. What exactly is a predicate, right? Well, right, you'll notice that we've talked about predicates before, right? So for instance, let's take this example. Well, I'm going to use Julia Roberts because she's in my notes, or Catherine Zeta-Jones if you prefer her. Julia Roberts is rich, okay? Now, in ordinary language, right, we would say that, let me give a different color here, a red, right? We would say that Julia Roberts here, this is the subject of the statement, of the sentence rather, and this, the last statement, is the predicate. So what exactly is a predicate? Well, a predicate is a quality, right? Let's put it here. Let me actually type it in here because I think it might be a little bit easier for you, right? A predicate is a quality, either essential or accidental, that is attributed to a subject, okay? So it's a quality. Now, let's go back here. I mentioned it's either accidental or essential, right? For instance, an essential quality of Julia Roberts is that she's a woman or she's female. That's essential, meaning that if she doesn't have that quality, she's not Julia Roberts. Richness here, of course, this statement is attributing a accidental quality. And I'm not saying it's an accident that Julia Roberts is rich, but just namely that in order for Julia Roberts to be Julia Roberts, she doesn't need to be rich, right? But of course, this statement is describing a quality of her as she exists today, hence it's an accidental quality. So a predicate is a quality either essential or accidental that's attributed to a subject. And what we're going to see here in predicate logic is we're going to symbolize both the predicate and the subject of each statement. So for instance, and what we're going to do here is the predicate is always going to be symbolized, right, as a front capital letter, right? And the subject here is always going to be symbolized as a back lowercase letter. Okay, so that means if we're going to symbolize this, Julia Roberts is rich, we're going to symbolize like this, RJ, right? Where this symbolize richness is attributed to Julia Roberts here, where the J stands for Julia, right? And by the way, this symbol, the person who's really responsible for predicate logic is a philosopher by the name of Gottlieb Frege. Very, very important logician here who really transformed logic and really is the one who came up with this. Of course, he didn't use this exact symbolization form. His symbolization form was very, very weird and difficult. But basically what we're teaching you here is the first order predicate logic form that everyone uses today. So this is how you're going to symbolize this. So let's give another couple of examples. Let's take the example, what if we said John is happy? How are we going to symbolize that sort of statement? Well, we're going to put H, capital H, J. HJ, that's how that gets symbolized. Let's do another one here. What if we said Socrates is a fool? Right? Or let's say is foolish, technically. Right? What if we said Socrates is foolish? Now, obviously, in philosophy, we don't believe that, but how do we symbolize that? We'd symbolize that with FS. FS, okay? Now, what you're going to see here is that we can utilize these entire statements and actually conjoin them using our operators, right? So for instance, I could say John is happy and Socrates is foolish, and that would look like this. H, J, here's our conjunction, right? And Socrates is foolish, right? So this is how you can conjoin them. So you're going to see here, right, that when I said earlier that the thing that's wonderful about predicate logic is that it combines the best elements of propositional logic with the best elements of categorical logic. We'll come to the elements of categorical logic yet. We haven't gotten to those yet. But we're just sort of looking at propositional logic right now. But that means that all of these basic connectives we've been looking at still apply. So we can create, and these are going to be called compound propositions, of course. Right, so let me give you an example here. And these are right from the textbook, so I'm not going to write them out. But for instance, we could say, what if we said this statement? If Paris is beautiful, then Andre told the truth, right? How do we symbolize that? Well, if Paris is beautiful, that's going to look like this. And I said, if Paris is beautiful, so that means we have a conditional statement. Then Andre told the truth. Well, okay, then that means T here for telling the truth. And Andre, here goes this. So it would look like this: B, capital B, lowercase p, conditional, capital T and A, right? So let's give another one here. Let's take a look at these. In fact, maybe it would be helpful actually just take a look at the book instead of me going through these. Whoops. Okay, sorry about that. So let's take a look here, right? You can see here's some of the other examples they give, right? Socrates is mortal, MS. Tokyo is populous, PT. The Sun Times is a newspaper, NS. King Lear is not a fairy tale. See, they actually give a negation here, right? So if something, if you deny a predicate, then you place the negation in front, right? So you get F, not FK. And then Birlos was not German. That's not GB, right? So let's get down here to some of these propositional statements, right? Let's take a look at these, right? If Paris is beautiful, then Andre told the truth, right? We already did that one. Irene is either a doctor or a lawyer, right? So that means that Irene is going to stay the same in both the subjects here, but the predicate changes, right? Either Irene is a doctor or she's a lawyer, right? DI or LI, right? Senator Wilkins will be elected only if he campaigns, right? So that would be Wilkins is elected. If Wilkins, let's see, hold on, let's say. If Wilkins is elected, then right? Wilkins campaigned, right? So that's how that statement looks like. Remember, only if means that you actually reverse the sides there. General Motors will prosper if either Nissan is crippled by a strike or Subaru declares bankruptcy. You can see they're slowly adding in complexity here, but the basic system applies that we learned in propositional logic. That's one of the reasons we spent so much time going over propositional logic and natural deduction and all of these rules and building proofs, so that by the time we got here to predicate logic, you would be really amply prepared to understand what this sort of statement means. The only new monkey wrench we've thrown into the situation here is that we're just now adding the symbolization for the predicates as capital letters, and the subjects get lowercase letters. Because originally we would have said N or S, then G, but now we're including the predicates additionally, okay? And here's, of course, another one. Indianapolis gets rain if and only if Chicago, right? Biconditional, and Milwaukee gets snow, right? Well, if Chicago and Milwaukee both get snow, that's going to be SC and SM, right? If and only if, right? It rains in Indianapolis, right? So that's how that statement gets built, okay? So we can build lots and lots of compound propositions, and the only difference here is that we're symbolizing, again, the subject here and the predicate here, okay? Let's see here. Now let's go here to, that's the basics of compound propositions, right? And you're going to see in predicate logic, if you ever make a basic statement, you're going to symbolize it like this, unless, of course, you have a universal statement. What about universals? Universal statements. Well, remember, in categorical logic, right, we had two forms of universal statements. We had all S or P, right, and we had no S or P, right? This is from categorical logic, so I'll just put CL here for categorical logic. So the question is, how are we going to symbolize something like this, right? How are we going to symbolize this? Well, we're going to introduce a new tool, okay? And this is where things maybe are going to start to build in terms of complexity, right? So we're going to build a new tool, or we're going to introduce a new tool, and this is known as the universal quantifier. Okay, the universal quantifier. Now, what is the universal quantifier? The quantifier, this is when you're going to place an X. An X is placed before a statement. Okay, so let's do this example, right? So notice here that when I say all S or P, what does that really mean? Well, it really means that if I have an S, that S is always going to be a P, right? Notice the language there. All S or P means if anything is an S, then it is a P, right? That's really another way of rephrasing the statement. So if we said no S or P, it would be if anything is an S, then it is not a P, right? Notice the language of then, right? We're going to use, and whenever we use the term then in proposition logic, we use the conditional, right? The horseshoe here. Or if you're using a keyboard, right, it looks sort of like that, right? But we're using the conditional. And what we're going to do with the universal quantifier is we're going to symbolize it like this. So let's just take this basic statement, all S or P. How does that get symbolized in predicate logic? It gets symbolized like this. X, SX, then PX. Right? Now you're thinking, wait, what are you doing here? Here's how you would actually linguistically understand the statement. This would be like this. The X here, right, is a universal quantifier, so it stands for anything in the universe, really. So if there's an X anywhere in the universe, if that X is an S, then that X is also a P, okay? That's really what that statement does. This universal quantifier says, here's the X, and it's saying if there's an X in the universe, that X is and that X is an S, then that X is also a P, okay? So what if we did no S or P? Right, how would that get symbolized? Well, again, since this is a universal statement, we're going to use our universal quantifier and place the X in front of it. Now, of course, anything with an X in front of it is going to be sort of related to anything that follows immediately afterwards with the parentheses. Now the parentheses are pretty important here, and you'll see why in later lessons. So let's go back to here. No S or P. This is going to look like this. If there's an X in the universe, if that X is an S, then that X is not a P, right? So we basically just add a negation in the front. And we now have a fabulous way of actually doing exactly what we did in categorical logic, except now we can use all of the benefits we had in propositional logic, right? And we have the benefits of looking at universal claims, right? Okay. Now, here's something that's important here. In terms of the symbolization we're going to use X, Y, and Z here as individual variables. These are individual variables that are always going to be allocated toward as quantifiers. Okay. Now, the reason we're saying this is because in logical notation, we're going to give right, we can have a y-axis and an x-axis and a z-axis. You'll come to it in a minute here, right? So that means we could technically also say this, y, sy, then not py. And this really just means the exact same thing here, right, as this. These basically say the same thing, except of course, where they're referring to two different things in the universe, right? Okay, so, but X, Y, and Z, we're going to reserve these as variables that we can always use, which means you can't use these to symbolize subjects, right? That's the important feature here, right? So, for instance, up here, remember, if we had, right, HJ, right? Well, let's imagine, for instance, if I said Xavier is a magician, right? Right. Normally it would symbolize like this, mx. We don't want to do that, right? We don't want to do that because we want to reserve the x here for the universal quantifiers as well as the y and the z. Okay. Now, remember these things. These can refer. They actually refer to anything in the universe. And that seems kind of crazy, but it's important because that's what it means for these to be universal quantifiers, okay? And of course, we could, in fact, use Venn diagrams to symbolize this whole thing. And maybe I'll do this here at the end here. But let's keep going here. Let's do some practice here because let's do some simple statements. What if someone says, for instance, all skyscrapers are tall? How are we going to symbolize this sort of statement, right? Well, we're going to symbolize like this. If there's something in the universe, this X, if that X is a skyscraper, then that X will be tall, okay? Now, some of you may be thinking, but wait a second. Didn't we say that subjects, right? All skyscrapers are tall. Didn't we say that subjects here should get symbolized just as lowercase letters, right? Well, this says that there's a skyscraper and that skyscraper is tall, right? This statement says this statement says that of all the things in the universe, if that thing is a skyscraper, then it's going to be tall, right? Which means that we're going to symbolize both subject and predicate here as capital letters, okay? Let's do another example here. No frogs or birds. No frogs or birds. Now, if you want, pause the video and see if you can figure out how to do this statement. It's going to look like this, really. X, right? If there's an X in the universe, if that X is a frog, right, then that X is not a bird, right? And that's what it's going to look like here, okay? Let's just do a couple more here. Oh, and I should mention, what is this whole thing called? This is actually referred to here as a statement function. Okay, so in the forthcoming videos, if I refer to a statement function, that's what this thing is. It's a statement function, okay? Now, let me go through and explain here, because I did talk about the variables here, and I want to give you a little bit more vocabulary, right? Let's say there's three key elements, right? Three key, almost just elementary elements here. The first are free variables. Okay, now free variables are those variables that occur in statement functions, right? But without a quantifier, they have no truth value and they make no definite statement or fact, right? So again, a free variable, right, are those variables that occur in statement functions, okay? Two, we have bound variables. Oh, I'm sorry, they occur in statement functions but with no qualifier. That sort of. I'm reading my notes here to make sure I say this correctly for you guys, and I misread it, right? So a free variable, these are variables that occur in statement functions, but there's no quantifier. Quantifier, not qualifier. But there's no quantifier, right? Whereas a bound variable is a variable that occurs within a quantifier. So let me give you an example here, right? So for instance, if I said, well, let's give this statement here, right? Okay, let's take this statement right here. Now, what's the rule? Typically, we should put a parentheses in front here. But if there's no parentheses, the x will always only apply to whatever immediately follows it. So I didn't leave an x there because I wanted you to see that, right? So that would say that this over here, right, this is a bound variable, right, because it's bound to the universal quantifier. And this over here is a free variable, right? This is a free variable, right? So that's really the difference between bound and free variables. Now, in terms of the third thing here to mention here are the parentheses. And I sort of jumped ahead, I guess. Right? The x can only govern what follows immediately after it or what falls in the parentheses that follow it, right? So for instance, if I say x, fx, then t, x, right? All of this is bound. The parentheses tell us what gets governed, right? And if there is no parentheses, it's just going to go what's immediately afterwards. It may be a good idea to just always include parentheses just to keep things clear for you, right? Okay, now that we've talked about universal statements, let's look at particular statements. Now, let's go back to and remind ourselves. In categorical logic, we had two types, right? Remember, we had two types of particular statements. We had some s or p, and we had some s are not p, right? So what we need is how are we actually going to symbolize this? Because remember, the universal, we can't use a universal quantifier for exactly the reason that, well, we're not making a universal claim. We're talking about one thing that exists, right? And that's the critical point. Remember when we looked at the existential fallacy, we talked about a philosopher by the name of Boole, right? And one of the things Boole said was that he talked about the existential fallacy, right? And this is going back weeks and weeks ago, if you've been watching this for weeks. But he talked about the existential fallacy, and we talked about this in categorical logic. And he thought that universals did not include within them a claim of existence, but the particulars like this, like these two statements, do include within them a claim of existence. So if we can have a universal quantifier, can we have an existential quantifier? And that's exactly what we're going to do. We're going to create something, or a new tool, right? This is our second new tool for today, is an existential quantifier, right? And really the existential quantifier looks very similar, except we're going to place a backwards e and an x, right? And that is going to be our symbol, and it functions the same way as these other ones, right? And it sort of looks like this. But wait a second, there's going to be a difference here. So the existential quantifier sort of looks like this, and just like the universal quantifier, it goes in front of whatever statement function is going to follow from it. Now, let's go back here and remind ourselves in categorical logic. how do we explain the language of this? If I said some S or P, I mean, right? Remember, if I say some S or P, right? And I could even symbolize it with the Venn diagram, right? Where I have two classes, right? And it says that if I have an S, that S is also a P, right? Or maybe use the better language here is there exists an X and that X is an S and that X is a P. But notice the language here that I just used. If there's an X in the universe that exists and that X is an S, that X is an S and it isn't a P. I use the language of and, right? Oh, you can't really read that very well. But you use the rule of conjunction. So here's how we're going to symbolize these things, right? So let me go back down here and symbolize them. So if we get some S or P, that is going to be transformed into this formulation, right? I'm going to add my existential quantifier here, and then I'm going to add this, Sx and Px, right? And so literally, how can you read this? In ordinary language, it looks like this. There is an X that exists in the universe. That X is an S, and that S is a P. Or in other words, some of the S's are P's, right? That's the formal language we're going to use. Now, what if you said some S are not P? How would you symbolize that? Well, right, you add your existential quantifier in the beginning, right, which says there's an X in the universe and that X exists, right? That X is an S and it is not, whoops, I made a mistake here. I wrote an S here, let me erase that. That X is an S and it is not a P, right? So that's how you're going to symbolize those things. Now let's go back, and I'm sorry this is taking a while here, but let's go all the way back here in categorical logic and remind ourselves of the square of opposition. Remember we had these statements, all S or P, no S or P, some S or P, some S or not P. Right? Well, now what we have is now utilizing, let's get a blue here. So now utilizing with the square of opposition here, you could see that we now actually can write it out using predicate logic. So it's going to look like this. Sx, then Px, x, Sx, then not Px, and then some x or p is going to look like this. Existential quantifier, Sx and Px, and then over here, some x or not, it's going to be existential quantifier, Sx and not Px. Okay, so this is the basically the long notation way of saying something like this. Now, the reason this is important and the reason we're doing all this, because remember on the back burner, we also talked about the idea that if you just make a basic claim like Julia Roberts is rich, right, you end up with RJ. Don't forget about this here, because what we're going to see here is that because we now have the universal quantifier and the existential quantifier, and we also have this tool set over here, we can now combine the insights of categorical logic and propositional logic ultimately in order to analyze very, very complex statements. Now, of course, just as a reminder, notice that whenever we do use a universal, right, which is up here at the top, right, this is universal. Notice we're using the conditional, right, and when we're talking about particulars, it's important we're using the conjunction here instead. Now that's an important thing just to remember. But I will say this, that it is still possible to have biconditionals and disjunctions and all sorts of complicated equations, right? We're just not there yet, but that's going to be coming, okay? So let's do some examples here, right? Let's say, what if I said that some women are CEOs? What if I made this claim? Now remember, since I said some, this is going to be a particular statement, which means I've got to include an existential quantifier, right? If I say some women are CEOs, then it's going to look like this. Well, if there's an X in the universe, that X exists. If that X is a woman, no, that X is a woman, and that X is a CEO. So we'll just put C here for CEO, right? And that's how you would actually write that statement, right? What if I said this? Some people are not stupid, which probably most people think they're not stupid. Some people are not stupid. How am I going to symbolize this? Well, it's going to look like this. EX, right? PX and not SX, right? Because what this says is there's an X in the universe, that X exists, that X exists, that X is a P, and that X is not an S, okay? And we're using that conjunction again, okay? Now, what's the trick in terms of translation? Now that we've gone over the symbols, the question, of course, is translation. How the heck are we supposed to translate this stuff? This stuff is very, very difficult. The key thing to remember here is translate the meaning, not the grammar, right? It's very, very easy, especially when you're first learning the first order logic here, to think that you have to translate the grammar. No, no, no. You're translating the meaning of a statement, right? So let's go here to the textbook and show you an example here from, I think let's go down here. You can see here, take a look at here, right? Here's the language they put for any X. If an X is an S, then it's a P, so on and so forth, right? So they give you the Venn diagrams, right? The Boolean interpretation, all those sorts of things, right? And here's the way they did the verbal meaning. There exists an X such that that X is an S and X is a P. Maybe that's a little bit easier than what I did, right? But the same symbols occur, right? Okay. And here's some of the examples they give. Some men are paupers, right? That's going to be MX and PX with the existential quantifier. Some diseases are not contagious, right? That's going to be existential quantifier DX and not CX, so on and so forth. I'm not going to go through all these, right? But let's go through these. And what I want to do here is, well, I guess since you're already looking at it, it's kind of difficult for me to do. Let me see if I can make this a little bit bigger for you. Okay, so take a look at this statement, right? If you could, try to ignore this stuff in the sidelines here, but take a look. There are happy marriages. How's that gonna look? That's an easy one, right? There are happy marriages. Notice it doesn't say some marriages are happy. It doesn't say that. It says there are happy marriages. But what's the meaning there? The meaning is, when you say there, is that some of them are happy marriages. So we're going to translate that really just as some S or P, the way we did our some S or P. What about this one? Every pediatrician loses sleep, right? So when you see the word every, think, what's the meaning of the statement? Well, the meaning is that ultimately they're talking about all pediatricians, which means we're going to add what? The universal quantifier. And that means that if you're a pediatrician, then you're going to be losing sleep. So that's our typical formation. This one's interesting. What about this statement? Animals exist. Animals exist. Well, right, notice here, this is just EX, AX, right? Because this is saying that because here, of course, they're using the term exist, which means they're obviously singling out existence, so we need an existential quantifier. Whenever a statement means to convey the existence of something, we need an existential quantifier, right? In this case, it's animals. And notice here there's no parentheses because the EX here is going to refer to just, or I shouldn't say EX, but the existential quantifier here is going to refer to only that which falls immediately afterwards. Maybe I'll make this a little bit bigger. Okay. All right, I think maybe you can see that a little bit easier. Okay, so let's go here. What about this? Unicorns do not exist. Unicorns do not exist. Well, they're talking about existence, so that means that we have to have an existential quantifier, right? We're talking about unicorns, but we're saying that it doesn't exist. Well, what we do here is we actually add the existential quantifier. We have our UX, right? But we just we put the negation in front of the quantifier. So we're negating the quantification of unicorns as existing. That sounds fairly complicated, but that's what it means, okay? Anything is conceivable. Now this is sort of difficult, right? Anything is conceivable. Well, it means that well, you're talking about anything, you're really talking about everything. And it's, well, you could be talking about everything. So we're going to include a universal quantifier here, right? What about this one? Sea lions or mammals? That's pretty easy, right? The question would be, is this a universal statement or a particular statement? Notice it doesn't actually say that. It doesn't say universal or particular. But you'd have to ask yourself, well, what's the meaning, right? What does this person mean? Well, if they're saying sea lions are mammals, they must be talking about all sea lions. So if they're talking about all sea lions, then we would include a universal quantifier. Notice here the next one. Sea lions live in these caves. Well, obviously not all sea lions live in these particular caves, which means we're talking about particular sea lions. Notice the term particular. If we're talking about particular sea lions, then we need an existential quantifier, right? Egomaniacs are not pleasant companions. Probably lots of people know this, especially people who are married to philosophers. Know this, right? Or politicians, right? Egomaniacs are not pleasant companions, right? Well, right, again here, the context is what ultimately allows us to determine how to interpret this. We're going to say that this is a universal claim because there must be talking about all egomaniacs. So we end up with this, right? Or in other words, you can imagine, how could you translate this? It'd be no egomaniacs are pleasant companions, right? That sounds exactly like no S or P. That's how the formulation looks, right? A few egomaniacs did not arrive on time, right? A few egomaniacs did not arrive on time. How is that translated? Well, we have, right, since we're talking about a few, we're talking about particulars, so we're talking about some that exist, right? So we have our existential quantifier. We're saying that there's an X in the universe, that X exists, that X is an egomaniac, and it is not one that arrives on time. That's what that means there, right? What about this? Only close friends are invited to the wedding. Only close friends are invited to the wedding. Well, that would be that, well, if there's, they're saying that of all the people who are invited in the universe, only close friends get invited. So that's a universal. So that's going to be X, LX to CX, okay? None but citizens are eligible to vote, right? Wait a second. The language there is, what does that mean? None but citizens are eligible to vote? It really means that all people eligible to vote are citizens, which that's a universal claim, right? Where it says if there's an X in your, if that X is eligible to vote, then that X is a citizen, right? Notice here, there's two more here we'll take a look at here. And I'm just going over these. I didn't want to write them out, but I'm trying to help explain them. I hope it's helpful. Right? It's not the case that every Girl Scout sells cookies, right? Notice there's two different ways to do this, and it depends on how you interpret the meaning of the statement, okay? So this one says that it's not the case that every Girl Scout, because of the first interpretation says that, well, they're saying it's not the case that every Girl Scout, every here is a universal. So that would be, if you're a Girl Scout, then you're selling cookies. The universal, it's not the case, negated in the front, right? Another possibility, it's not the case that every Girl Scout sells cookies. You could interpret that as saying some Girl Scouts don't sell cookies, right? And that's what it would, then you could use an existential quantifier here, right? Where you'd say, there's Girl Scouts that exist, but some of those things that exist are Girl Scouts, and they're not things that sell cookies, or not people that sell cookies, okay? And the same thing goes here with the last one, right? Not a single psychologist attended the convention. You could interpret that in two different ways. You could interpret that as saying that no psychologist attended the convention, or you could interpret it, when that's what this says right here. No, this is basically the no S or P formulation. Or you can say not a single, because then this word single seems to say that, well, there's no particular psychologist that attended the convention, and that would look like this statement, right? It's not the case that there are psychologists and those psychologists also attended the convention, right? So there's different ways to do this. The tricky part that some of you are going to have here, I think, is noticing the negation in the front of the quantifiers here, okay? Let's see here. So let's go. I want to go over one more thing here, which is the disjunction, right? Whatever happened to the disjunction? Because remember, we've only been looking at the conditionals and the conjunctions. But what about the disjunction, right? Our either or operator, which we've been symbolizing with the lowercase v, right? What about that? Well, here's the thing to remember. When using a quantifier, a conjunction will mean that something is categorically equivalent or not, right? So let's go over here to the conjunction, right? Which looks like this. We do our little dot. And this means something is categorically equivalent, right? Right, so the conjunction means that it's categorically equivalent, right? Um, but what about the disjunction? Of course, the disjunction means that something may or may not be the case. So let me give you an example here. Right, this is an either or. It's either categorically equivalent or it's not. Whoops, how come I... Sorry about that. All of a sudden my computer is wigging out on me. Okay, it means either or, right? Not equivalent, right? So what are we going to do here? Well, let's do this statement. Here's some examples. What if we said this statement? Oh, sorry, there's something going on with my computer here. I'm not sure what is going on. Okay, so let's go back here. Let's give this example. What if I said ripe apples? Okay, hold on a sec. I'm going to have to type this out because for some reason the computer's not working. What if I give this statement? Ripe apples are crunchy and delicious. Right, what about this statement here? Ripe apples are crunchy and delicious. How should I symbolize this, right? Well, here's how we're going to symbolize it, right? And this is going to be a bit complicated, but hopefully you'll get it, right? Ripe apples, it's going to look like this. X, and let me write this out and I'll explain it. That's a bracket. Rx and AX, then CX and DX. Okay, so why did I symbolize it like this? This is going to say ripe apples. This says that if there's, I realize this example didn't use the disjunction here. I'll go back and give you an example for the disjunction here. I pulled the wrong example, but that's all right. This is a complex statement, right? Ripe apples are crunchy and delicious. This is going to say if there's an X in the universe, that X is an R and that X is an A, right? It's ripe and it's an apple, right? Because not all apples are ripe and not all ripe things are apples. So if it's ripe and it's an apple, then, right, it's going to be a crunchy thing and it's going to be delicious, right? And the reason we gave it a universal quantifier here is because what's the meaning? When someone says ripe apples are crunchy and delicious, they mean that all ripe apples are crunchy and delicious. And so that's why we've symbolized it in the way we have. Let me go back here and give another example here. What if I said... I said that some apples are green and tasty. What about that example? So let's type that one in and see what that one looks like. Some apples are green and tasty. Whoops. Some apples are green and tasty. How should we symbolize this? And this is where we're going to get our disjunction. You're going to see how we can use the disjunction here. Okay? If some apples are green and tasty, well, obviously some means I'm going to need an existential quantifier because I'm not talking about all apples. Some apples are green and some apples are tasty, right? So how should I translate that? Well, here's how I should symbolize it, right? I'll need a bracket because I want this existential quantifier to actually refer to the entire statement function I'm about to write, right? I'm going to say AX here. Right, and so I'm saying there's an X that exists in the universe. That X is an apple, and right, parentheses, that X is either green or it's tasty. Right, and you can see here in this case I used the disjunction. Right, I use the disjunction. Why did I use the disjunction? Well, think here for a minute about the meaning of this statement that some apples are green and tasty. Some apples are green and some apples are tasty, but there are some apples that are not tasty, right? And some apples that are not green, right? For instance, I can have a red apple that is also green and tasty. I can also have a green apple that's not tasty. So when I say some apples are green and tasty, the question is, I didn't symbolize this with an and here because I looked at the meaning of the statement. And the meaning of the statement really means, well, it's going to be green or tasty or both, right? Remember, when the disjunction here also refers to, is an inclusive disjunction, meaning it can be one or the other or both. So this is an inclusive disjunction. And so that's why I used the disjunction here, okay? So that's an example of using the disjunction. So let's give another example here that I think might be helpful. And one of the things you'll find is that in some cases, there are times in which we can use two different translation examples. So I'm just going to do a couple of examples here. And I'm sorry because I know this video is getting fairly long here and probably a lot of you have already tuned out. But it's pretty important that you get used to doing these. So let's do one. Peaches are edible unless rotten. How should I symbolize this statement? Peaches are edible unless they're rotten. Well, right, think about the statement. This is a categorical statement, really, because I'm talking about all peaches are edible unless they're rotten, right? So that would look like this. Now remember, I'm not saying that this statement's actually true, but it is a categorical statement. Well, there's one way we could say is, well, it's universal, so I need my universal, right? I'm going to put a bracket here. And then say, if there's an x in universe, if that x is a peach, right, then what? But here, edible and less rotten. How do we make sense of this unless? We're going to say, then, if it's not rotten, then it is edible. Okay, close bracket. Right, so if there's an x in the universe, if that x is peach, then if that x is not rotten, then it is edible. Right, that's one way of interpreting it. There's another possible version too. Right, and this goes back to our use of the disjunction. You could say, if there's a peach in peaches, right, if there's an x in the universe, if that x is a peach, then that x is either edible, right, or it's rotten. Right, so I could use the disjunction here instead of giving the negation and the conditional here, right? You basically just have to go through these very, very slowly. So let's take a look here at your homework and see if we can do a couple problems from your homework here before we move on, okay? Before I close the video and finally allow you freedom to escape, right? And you can see here they have ones about green avocados are never purchased unless all the ripe ones are expensive. You can see this. In fact, you may want to pause this. I would encourage you to pause this video, read these statements, and then sort of see if you can understand the translation. Notice in this one, right, if Elizabeth is a historian, then some women are historians. Notice the second part of the compound statement is a particular categorical claim, but the first part is not. So notice we have HE, where if Elizabeth is a historian, then it's the case that some women are historians, right? So that's what it looks like. So you can combine these. Notice in this, here I'm not talking about it, but notice in this one, either everything is alive or Bergson's theory is not correct, right? We have, notice the AX, since this is here, it only, the universal quantifier only applies to the AX, and that's why we have not CB. Either everything is alive or Bergson's theory is not correct, okay? So you can take a look at those. And I encourage you to read through these slowly. But you're going to see here how the homework exercises work if you're using the textbook, right? Right. Elaine is a chemist. They're going to want you to basically avoid negation signs preceding the quantifiers. The predicate letters are given in parentheses. But you can do that, right? Because we've done it. Elaine is a chemist. That's going to be C E, right? Nancy is not a sales clerk. That's going to be S N. You can see on so on and so forth. But let's go down here. What about this one? Some grapes are sour. How's that going to look? Well, that's going to be well, some grapes are sour. Let's do it for you, right? If we do some grapes are sour, that's going to be, right? Some means existential quantifier. If that thing is a grape and it's also sour, right? Some grapes are sour. So that's how that's going to look like. Tigers exist. How's that going to look like? Well, tigers exist here. That's going to be existential quantifier, because I'm talking about existence, TX. Okay? Not too difficult, but you'll see that when you get to the bottom here, they get more and more complicated, right? And then here, right, you can see here, there's actually quite a few of these. And by the time you get to the bottom, they get very, very complicated, right? See here, they give you all of these different variables. If the scientists and technicians are conscientious and exacting, then some of the mission directors will be either pleased or delighted. You can see this is one that's going to be more difficult, but it's ultimately very important practice. But notice with predicate logic, we can actually now do something really radical. We can take a statement this complicated and actually be able to symbolize it in all of its particular elements. And we can really do that in a way, in a really fine-tuned way that we were never able to do before. Okay. Now, what are some of the things to remember? And then I'll turn the video off and give you your life back. Some of the things to remember. And in our next video, we're going to go over some of this. Is number one, right, is remember that X, Y, and Z, these are reserved variables. So don't use these. We're reserving these variables for our quantifiers, right? The second thing, and we're going to talk about this, is that all of the rules of implication and replacement still hold. And what we're going to do in our next video is I'm going to show you how to use these rules and the rules of implication. We're going to introduce a couple new things in terms of a couple new rules, but all of the basic rules of implication still hold. So like modus ponens and modus tollens, all that still is valid. And the last thing here is that all other letters can be used. So you have all the rest of the alphabet to use, but X, Y, and Z, we're going to keep these to ourselves, okay? So anyway, I'm going to conclude the video there. I apologize, there's a couple hangups, and I apologize for the length of this video. It's almost an hour long here. But I hope you can see here that it was really important here with predicate logic to really lay it out, but you've already worked on the basic mechanics of all of this stuff, so I'm hoping that it won't be too difficult. So anyway, thank you for watching, and I look forward to seeing you guys online. Okay.